designing a data structure for range MEX queries with frequent point updates and sublog time per query. The MEX of a set is the smallest non-negative integer not in the set. Here are two quick examples. First set, 0, 2, 3. Second set, 1, 2. Now, a range MEX query on an array chooses a subarray, collects the values that appear there, and reports the smallest non-negative integer not present. Here is an array. We query the range 1 to 4, inclusive. The values in that range are 0, 2, 1, and 3, so the MEX is 4. Point updates change a single array position. Suppose we change index 2 to 0. The set of values in the same range may change, and so can the MEX. A key identity. Fix a range from L to R. For any value x, it appears in the range if and only if the last occurrence of x at or before R is at least L. We show occurrences of x equals 1 along the index axis. If the last mark before R is left of L, then x is missing in the range. Therefore, MEX of the range is the smallest x for which the last occurrence at or before R is strictly less than L. We store, for each R, the last position of every value at or before R in a tree over the value domain. Each leaf corresponds to a value x and stores last sub-lo R of x. Each internal node stores the minimum of its children. To answer MEX for a given L and R, we descend from the root. If the left child minimum is smaller than L, the answer lies on the left. Otherwise, it lies on the right. We stop at the first leaf that violates the inequality, which is the MEX. To support frequent updates, when an index P changes from old value to new value, we update the position sets for both values and refresh last occurrences at R, producing a new version of the tree. Using persistence, each update builds a new version with logarithmic changes over the value domain. Query time is logarithmic in the value universe with a binary tree. With higher branching factors and word-level bit sets near the bottom, the height becomes small and the practical query time becomes sublog, and in theory can reach log-log of the universe using Van Emd-Boas style layouts. A practical acceleration is to store a small prefix bit set for values from 0 to be -1 on each relevant node. When the union bit set in the query range is full, the MEX exceeds B, and we jump to the tree search among higher values. Otherwise, we find the missing bit in O of 1. End-to-end, array, and range. Collect presents in the range. Find smallest missing in the small prefix by bit set. If full, jump to the high-value search in the value tree. Summary. Persistent tree over values stores last occurrences by R. Query. Descend by minima to find smallest x with last sub-lo R of x less than L. With small prefix bit sets and Mulchieri or Van Emd-Boas layout, the query time is sublog in practice and log-log in theory. Thanks for watching.